Space curves. Suppose that f, g, and h are continuous real-valued functions on an interval I, then this set C of all points with coordinates x, y, z in space, where x equals f of t, y equals g of t, and z equals h of t, where t varies throughout the interval I, is called a space curve. The equations in the equation 4.1.3 are called parametric equations of the curve C, and t is called a parameter. We can think of C as being traced out by a moving particle whose position at time t is the point with coordinates f of t, g of t, h of t. If we now consider the vector function r of t with the components f of t, g of t, h of t, then r of t is the position vector of the point P with coordinates as the component functions of the vector r on C. Thus, any continuous vector function r defines a space curve C that is traced out by the tip of the moving vector r, as shown in the figure. Let's consider a two-dimensional vector function with component functions f of t and g of t, where f of t equals t squared and g of t equals t. Now, if t is increasing from negative 3.5 to positive 3.5, then we get the position of the particle at different times as shown in this figure. The point has x coordinate, which is equal to f of t equals to t squared, and the y coordinate of the point P is given by the function g of t, which is equals to t. Now, if we connect all these points, we get a curve as shown here. Now, if we connect the point P with the origin by a vector, then the position vectors of these points are shown in this figure. Therefore, the curve is being generated by the tip of the position vector of the point P, as we see in this figure. Let's have a look at an example. We need to describe the curve defined by the vector function r of t with components 1 plus t, 2 plus 5t, and negative 1 plus 6t. The corresponding parametric equations are x equals 1 plus t, y equals 2 plus 5t, and z equals minus 1 plus 6t, which can be written by eliminating the parameter t as shown here. If we remove the parameter t from all these three equations, we get an equation like this. And we recognize that these equations are the parametric equations of a straight line passing through the point with coordinates 1, 2, -1 and parallel to the vector with components 1, 5, 6, as shown in the denominators of the equations. Alternatively, we observe that the vector function can be written as r of t equals some vector r sub 0 plus some vector v times the parameter t, where r sub 0 is the vector with components 1, 2, -1, and v is the vector with components 1, 5, 6. This is the vector equation of a line passing through the point with coordinates 1, 2, -1 and parallel to the vector v. Let's have a look at another example. Describe the curve whose vector function is given by this, whose first component is cosine of t, the second component is sine of t, and the third component is just t. The parametric equations of these curves are x equals cosine of t, y equals sine of t, and z equals t. Now, after eliminating the parameter t from the first two equations, we find x squared plus y squared, which would be equal to cosine squared t plus sine squared t, which would give us 1 for all values of t. So, the curve must lie on a circular cylinder. The point x, y, z lies directly above the point with coordinates x, y, 0 on the xy plane, which moves counterclockwise around the circle x squared plus y squared equals 1 in the xy plane. The projection of the curve onto the xy plane has the vector equation with the first two components as the same vector components as given, but 0 as the third component. Since z equals t, the curve spirals upward around the cylinder as t increases. The curve is shown in the figure. It's called a helix. This shape of helix occurs in the model of DNA, deoxyribonucleic acid, the genetic materials of living cells. In 1953, James Watson and Francis Crick showed that the structure of a DNA molecule is that of two linked parallel helixes that are intertwined, as shown in this figure. Let's see the interactive figure of the circular helix, defined by the vector equation with the component functions f of t as cosine of t, and g of t as sine of t, and h of t equals to t. If t is increasing from 0 to 4 pi, then the point A has the position vectors as we see in the figure. So the points generate the helix. The helix is lying on the circular cylinder. Now we can also see the position vectors of the point A at different moments.